Welcome back, everybody. And this is the second half of the lecture where I talk a bit about what happens over the course of a glacier's flow. This is kind of a bit of a hydrology mini lecture. Now I will talk about how the glaciers flow, like what mechanism they use in the next lecture. But glaciers are really interesting because in Antarctica, they very much take the place of liquid water. Now, there is some liquid water in Antarctica, and interestingly, a lot of that is below the glaciers. One point I want to address again is the existence of subglacial lakes, like Lake Vostok. And Lake Vostok is an example where you have extremely thick ice, and that thick ice causes the pressure to build up. And something I mentioned before briefly is that if you change the pressure, that will change the melting temperature of water. If you increase the pressure, the melting temperature will drop. That means that you can have liquid water at lower temperatures than you would otherwise have. So even though it's cold that the water would normally freeze, there's so much pressure underneath the ice from the overlying ice that you have a little bit of liquid water. And so this pressure, and in some cases also the heat of the Earth, allows for a number of lakes to exist underneath the ice, especially in some of the parts of the East Antarctic ice sheet where the ice is especially thick. And in some cases, you actually have water flowing between the lakes. You have subglacial lakes, and then they're connected by little channels. You actually have something resembling an under ice network of lakes and rivers. And relatively little is known about the movement and dynamics of the water in these subglacial lakes. It's a lot harder to study how the water moves from one lake to the next than it is to do so if you don't have several kilometers of ice covering everything. Also, there are some concerns about contamination. There's concerns that extremophiles that don't live elsewhere on Earth might live in these lakes, and we don't want to contaminate them and wipe them out. This is one reason why people look to Antarctica when thinking about how life might exist on other celestial bodies other than the Earth. What if there is life on the moon Europa, for example? But Lake Vostok is the largest of these lakes. It is the sixth largest lake in the world by volume. It is actually between Lake Malawi, which is one of the African Great Lakes. And if you remember, the African Great Lakes lie along the Great Rift Valley, where you have a divergent plate boundary spreading out. And so it's between Lake Malawi and Lake Michigan in the US. So it is actually, there's slightly less water in Lake Vostok than there is in Lake Michigan. So even though there's not overall a lot of liquid water in Antarctica, there is still a decent amount under the ice. However, most of the overall flow of water in Antarctica occurs via glaciers flowing. And the glaciers move very slowly. They actually move kind of like the asthenosphere, which is the part of Earth that moves that is solid but plastic and flows as a result of that. The solid plates made of rigid lithosphere float on top of the asthenosphere, which is a solid that can flow, just kind of plasticky. And glaciers are doing the same thing. Glaciers involve the slow movement of ice. And in the next class, I'll talk a little bit about how that involves the crystals of ice actually rearranging as this happens. But within ice sheets, you have noticeable currents of ice where the ice is moving faster. Ice streams are where the ice is flowing fastest, and ice streams are often in the middle of a glacier. Why does this often occur in the middle of a glacier? Well, so in the middle of a glacier and also on top, as opposed to the part that scrapes the rocks, you have less friction. The ice in the middle is not really in contact with the rock on either side as much if the glacier is flowing through a valley, nor is it in contact with the ice on the bottom. So often the center of a glacier flows fastest, and glaciers are a lot more affected by friction than liquid water is. There's much more resistance to flow in glaciers than there is in liquid water. So these streams can be quite noticeable. Now they're present. Now it's true with liquid water also that if you have a river, the water is going to be flowing fastest in the center. This can be quite distinct in glaciers, though, because solids have an intense resistance to flow. This map is actually showing how different parts are flowing faster. And you will notice that the ice does start to slow down a little bit as it starts to slow down a little bit as you have more mountains surrounding the ice, as you have more contact and thus more friction with the rock inside of mountains. Of course, you'll actually see that in this diagram of the ice streams that are feeding into the Weddell Sea, you'll notice you have fast-moving ice out in the center of the ice shelf where you just have ice that is not in contact with the land at all. As we'll talk about, the ice shelves are the extension of the glaciers that flow over the ocean in places like Antarctica, where even along the coastline, you still have so much accumulation of snow that the glacier still has a bit of steam to it. The glacier still is going to keep flowing over the ocean until eventually the latent heat from the water will cause it to start breaking up. But this is also a good example of how this is a good illustration of how the ice flow in the West Antarctic ice sheet is pretty convergent. A lot of it is flowing into the Weddell Sea here. And that's where a lot of these ice shelves, like the Larsen ice shelves, which are some of the ice shelves that have experienced dramatic collapses over the last couple of decades, as well as the Rhone ice shelf, they're all feeding into the same ocean. Now, interestingly, ice can form a waterfall. You can have an ice fall where you go from having a relatively gentle slope to having a steep slope. I got this picture in the dry valleys of where ice is kind of just falling from the polar plateau from the East Antarctic ice sheet and then going ploop into the dry valley. And then there's not enough ice flowing in here to keep it accumulating. So it kind of just comes to an end. But sometimes ice falls are one step along the process. It depends on how much accumulation is going on. But like a waterfall, an ice fall forms from sudden steepness. And you'll notice how the ice in this picture on the right looks like it's full of cracks. Those are crevasses, which form when glacial ice comes under intense stress. And instead of the ice crystals rearranging, the ice breaks. The ice becomes full of cracks. And these cracks are really dangerous because it's quite easy to fall into them. They can be very deep. We'll talk a bit more about crevasse formation and about the dynamics of glacial movement and how that leads to crevasse formation in some cases. That's a topic for next class. Now, I've been talking a bit about what happens when glaciers meet the sea. So, what does happen? Glaciers that reach the ocean behave in a number of different ways. An outlet glacier is any glacier that reaches the ocean. A specific type of outlet glacier is known as a tidewater glacier. That is a particular type where the terminus of the glacier is floating on the ocean and where it is moved up and down by the tides. Now, if glaciers are flowing with enough volume, like if there is enough snow accumulating on the coast still, the ice will continue to flow over the ocean. It'll flow out from the coast and out towards the open ocean. And that is what makes up the ice shelves in Antarctica. Those are generally permanent features of the surrounding oceans. And they will, even though the ice does go a bit over the ocean, it will break down faster than it does on land because the ocean has more latent heat in it than does the land. The ocean absorbs a lot of heat without changing temperature necessarily, but it can then pass on a lot of that heat to the ice in the glacier, and the glacier will eventually start to break up. Ice sheets, when they break up, that is known as calving. It's basically when a large glacier is breaking up into tiny pieces, it's kind of like, oh, the glacier is sort of giving birth to lots of tiny glaciers, even though that's not completely accurate, but you get the idea. And calving is sort of actually where glaciers end their lives, even though it's named after cows being born, because when the glaciers calve, they become icebergs. They become little bits of ice that, now that they have more surface area exposed, will start to melt faster. The sea ice is completely separate from all of this. It forms on the surface of the water in the winter and then melts in the summer, and it forms from the seawater. It doesn't form from the ice that is accumulating on land far from the ocean. Now, outlet glaciers are common in Antarctica because you have so much snow, or because you have so much, it's so cold and you have glaciers accumulating to the point where they can reach the ocean. And we have an outlet glacier here from a non-Antarctic example. This one reaches the ocean and terminates there instead of forming an ice shelf, excuse me. Now, this is the Ferrar Glacier, which is where the East Antarctic ice sheet starts to approach the Transantarctic Mountains near the edge of the continent and starts to be more constrained by them as it flows through the valleys. And you'll notice in this next diagram that you'll see how it's becoming kind of channeled. You have the East Antarctic ice sheet channeling ice through the valleys in the Transantarctic Mountains, and it ends up going out to the Ross Ice Shelf, where that ice will flow over the ocean for a bit until the ice starts to break up as icebergs. You really do want to think of glaciers as rivers of solid water, and streams of ice will flow together. Streams of ice will also diverge in some cases. They can do either, depending on the topography. And part of the Glaciers lab is going to be sort of studying how glacial flow is affected by the presence of rock in the area. Now, tidewater glaciers are one specific type of outlet glacier where the edge of the glacier sticks out over liquid water, and this is often going to be noticeable in areas where you have a big tidal variation, where you have a big difference between low tide and high tide. At high tide, what will happen is that the end of the glacier will get a bit of a lift from the higher water, and this will actually cause the glacier to flow slightly faster because the lift from the water being higher will reduce the amount of friction the glacier has with the ground. But when we get to low tide, the glacier will start to flow more slowly again. The water will subside, the lift factor will be gone, and instead of being lifted up, the glacier will just be plopped back down on the rock, and it will be grinding against the rock again. Tidewater glaciers have been extremely heavily affected by global warming because they're in contact with the ocean, which is getting warmer. Now, where instead of terminating at the ocean, the ice continues to flow out over the ocean, you have an ice shelf. An ice shelf forms if the glacier continues to flow over the surface of the ocean, and since water, when it freezes, is actually less dense than liquid water, this can happen. The accumulation of the glaciers in Antarctica is still stronger at the coast than the ablation or loss of the glaciers. And this is the interesting thing. One of the interesting things about the glaciers here is that you have the ice shelf is actually attached to the ice on land. It's literally an attachment to the main glacier sticking out over the ocean. It is part of the ice flow related to the ice sheets in Antarctica. Of course, they will break up eventually, and you have a sheer cliff out over the ocean where the icebergs break off from it. Now, ice shelves are considered permanent on a human lifespan. However, since humans are changing the climate to an unprecedented degree, we are seeing much more breakup with some of the ice shelves, particularly those in the Western Arctic area where the ocean is warming faster. And this is what I mean. This map is actually showing a comparison of what the glaciers look like in Greenland versus Antarctica. And in both places, you have accumulation near the center. Now, in Greenland, you start to enter the zone of ablation, or where the glaciers are breaking up, before you get to the edge of the continent. So in Greenland, the glaciers are breaking apart either before they get to the ocean or right at the edge of the Greenland continent. Now, in Antarctica, you have so much more ice and so much more intense flow of ice that you still have accumulation, this green zone occurring as far as the shoreline where the ocean meets the bedrock. And you get more melting when you reach the ocean because water conducts heat better than does the bedrock. And you'll have melting underneath the base of the ice shelf, and that will overall weaken it until once it reaches far enough over the ocean, you'll get iceberg calving. You'll get little icebergs breaking off. And those icebergs melt a lot more quickly than does the main ice shelf because the icebergs have so much more surface area exposed to water as well as to air. And we have several major ice shelves in Antarctica. We have the Ross Ice Shelf, which is near McMurdo Base, and that covers essentially the entire Ross Sea. It is a massive accumulation of ice. You have the Roan Ice Shelf and the Weddell Sea. Then you have a number of smaller ice shelves covering bays in Antarctica. There is very little open water right next to the coast. In Antarctica, you're generally going to be on an ice shelf, or you're going to have a lot of sea ice right along the coast. The only exceptions are going to be where katabatic winds are blowing enough that you're going to have coastal polynyas opening up. And coastal polynyas often actually form between the gap between the ice shelf and the non-permanent sea ice. Now, with calving, the calving just refers to to glaciers breaking up in general. And calving can refer to, say, when you have a glacier on land, you have it kind of falling on land. In Antarctica, glaciers largely break up over the ocean, and the ice breaks up into icebergs, smaller remnant pieces of the glacier, until the icebergs melt. There have been some pretty alarmingly big breakoffs of large pieces of some of the ice shelves. You'll notice that this is a bit of one of the ice shelves breaking off, and if you look at the scale on here, this piece is, I would say, about 200 kilometers long. That's the size of a small US state. We are seeing pieces of the ice shelves that are as large as some of the smaller United States states, like Delaware and Rhode Island, starting to break off. We are starting to lose bits of the ice shelves that are as big as Delaware and Rhode Island. Those are not very big states, but that is a lot more of these ice shelves than we are normally used to losing. The calving is intensifying. The water is getting warmer, and that is causing the ice shelves to break up faster than we would expect, because normally we don't expect them to break up in big pieces like this. Normally, we expect lots of tiny pieces, not enormous chunks to come off. And that is something we will talk more about during the climate change unit. I want to mention that sea ice has nothing to do with glaciers. Sea ice is simply the water forming it's simply the ice forming when seawater freezes. Again, it is freshwater because the salt does not go into the ice. Sea ice forms on the surface year-round. It fringes the land and also forms a little bit of a fringe on the ice shelves. It becomes a lot more expansive in the winter, and it plays a number of important roles. We talked about Antarctic bottom water and how sea ice formation triggers Antarctic bottom water formation, how krill and algae depend on sea ice during the winter, and how sea ice helps keep Antarctica cold. Sea ice has higher albedo than ocean water, which is darker. Sea ice reflects solar radiation. Ocean water absorbs it. So when Antarctica has a lot more sea ice surrounding it, more solar radiation is reflected. So the decrease in sea ice formation from climate change is already starting to have an effect on all of these important processes. I will note that this does not show a reduction in sea ice over the years. This is between seasons. So this is February, so basically summer 2006, and then September is the winter. So this shows you just how much the ice can get more expansive between summer and winter. However, we are seeing the extent of the winter sea ice declining in some areas. That is very true in the Arctic. It is also true in Antarctica, just not quite as uniformly. And in our next class, we'll talk about how glaciers move, the different methods the different mechanisms by which glaciers are transported, as well as how glaciers erode the ground underneath them and surrounding them. Again, sorry for recording this on the late side and also for doing this recording so late at night. Thank you for being patient, and I will see you for the next lecture soon.